Okay, so what we really want is this voltage that we're calling V out. Okay? And we already know this voltage, and we know this voltage. So Tom, what are we going to do?
Well, why don't we do KVL again?
Wait, KVL, but there's nothing connected. Can you do KVL?
Sure. I mean, there's still nodes, and there's still a potential difference between the two.
That's true. There is a potential difference between any 2 points on the circuit, right? So, okay. So how about, let's do it my way. Is that okay?
Yeah, that's fine.
So we'll do clockwise, and we'll say minus VR2 plus V out plus VR4 equals 0. And so V out must equal VR2 minus VR4. I guess that kind of makes sense if you think about it as height differences, right? If from here to this point on the left where the plus is say, if you think about it heights again, if it was 4 meters high and this one was 3 meters high, then the difference between the two would be 1 meter, and that would be the height difference between the two. So KVL does work. It's just like kind of elevation like we did before. All right. So we can write this out. So V out, and let's see. So we had R2 over R1 plus R2, and we multiplied that times V in, but that's the same. And so we're going to say R4, R3 plus R4 plus R4. And that's going to be times Vn. Aha.
So if we look at this expression, what looks like is happening is that Vn is being divided by the first branch, and it's being divided by the second branch. And the actual output, the difference between those two terminals, is the difference in the division.
Great, that works. So in our circuit, and very commonly in these Wheatstone bridges, we'll pick the resistances so they're all the same nominal value. So let's say that most of these, and we'll leave R4 with its own label just to talk about it, but let's say all of them were R, the same value. We picked them all. So then it would be R divided by R plus R. So that's 1/2, right? This goes to 1/2, provided that all the resistors are R. And this would go to R divided by R plus R4. And we kept it that way. Yeah? So we've got R4 divided by R plus R4. Okay. So it's exactly what you said. So, if these are both the same, then this would always be at half of Vn voltage. And then whether this is at half or not depends on whether R, if R were exactly equal, if R4 were exactly equal to R, you'd have a half on the side, and you'd have half minus a half is 0, right? Because then they'd both be exactly the same height. If this changes a little bit up, then this number will be bigger. And if it changes a little bit down, if R4 changes a little bit down, because remember this is going to be our variable resistor, then it'll be a little bit smaller. So this is what we're going to do now, actually. We're going to go and we're going to build a circuit that has 3 resistors of the same value. And the fourth is going to be our sensor. And we will have picked our 3 fixed resistors to be approximately the value we know the sensor kind of is at when it's not being touched, right? Is that fair? And then we'll pick a Vn that comes out of our battery somehow, basically a fixed voltage. So that's the Wheatstone bridge. So I've got one question for you, though. It seems easy enough, but I've got a couple things I want to point out. So the first one is that you might wonder why we just don't use a voltage divider, right? Why have this business of having that other thing at 1/2 if we just have a voltage divider? And that requires a little bit more math to talk about. And so we've provided a link for you to kind of follow and read up on it. But I want to point out here an idea that is very useful moving forward, and that's sensitivity. And this is something that does have a technical definition for sensors, for things that are interacting with the real world. And basically the way to think about it is it's the change in the output divided by the change in the input, okay? So something that is more sensitive has a bigger change in the output for a given change in the input. That would make sense, right?
Yeah, so in this case, our input is the resistance.
That's right. So
R4.
we could write this in that way, right? Our input would be a resistance, and our output would be, say, V out. So we could write, for example, the delta in V out as divided by the delta for a given change in R4. But in many cases, the way you want to do this is formally, you want to write it as a derivative. So you have dV out over, so dV out dR4, or right? The derivative of V out with respect to R4. This is a detail that we delve into in the link, but it's good to keep in mind that's really why you build these things, because this happens to be a pretty sensitive circuit for this kind of change. Next thing I want to point out. We kept making use of this sort of idea that there is call it a fixed point. I'm almost loath to use that word, but there's a sort of ground level here that we were basing all of our analysis off of. And in fact, this notion is going to come back, and we're going to touch on it very soon in one of the next videos. But this idea that there is a point from which we reference everything else is going to be very, very useful. And that's where some of you have heard this is called ground. But I want to point out, and I'm going to kind of be tedious and point it out again in the next video, that ground can have slightly different meanings as you work through electrical engineering. And so we're going to give you one of them and kind of work through, but it's sort of very similar to what we've done, is picking this sort of reference point. Okay, I think we're ready to build our circuit, right? We should just build this, and now what we're going to try to do is build this and then feed this V out somehow into our processor, right? I suspect we're going to have a little surprise there, but
yeah. Well, why don't we go back to the breadboard and see what we get?
All right, let's go build this.